All right, so for our next talk, we are going to switch focus a little bit to iOS, and Yarden is going to be talking about unpacking the iOS sandbox. So round of applause for Yarden.
Yeah? Okay, perfect. Hi, hello everyone. I'm very happy to be here and share with you a little bit from my knowledge on the iOS sandbox. So about 2 years ago, my manager came to me and told me, there is something I need you to do. I need you to parse the iOS sandbox profiles. At the time, I was pretty new to iOS. I didn't know what it meant to parse an iOS sandbox profile, and honestly, I'm embarrassed to say I wasn't even sure what iOS sandbox really was. He gave me some starting points, but I can say for sure we didn't have a lot of information at this point. But one thing he did mention was an old tool called Sandblaster. So today I'm going to walk you through my journey from not understanding the importance of this task to completely believing in why it's worth investing time in it. My name is Yarden. I work at Celebrite as an iOS security researcher. I've been with the company for about 7 years or so. I started as a decoding researcher, and for the last 3 years, I've been focusing on iOS security. My goal here in this talk is to give you the information I wish I had when I started this project, and to show you why I believe this tool is so valuable for our iOS researchers. So here is what we are going to cover today. First, we'll start by understanding what the iOS sandbox actually is. Then we'll talk about why it matters and how understanding it benefits us. After that, we will dive in a little bit into the unique Sandbox profile file format. We will look at Sandblaster usage, the challenges we faced and how we managed to overcome it. And finally, we will wrap up with some changes introduced in iOS 18. So the iOS Sandbox is a security mechanism implemented by Apple. And to be honest, it makes our life much, much harder. Apple is well known in integrating complex layered security mechanisms to enhance the protection of their system. The sandbox is designed to protect system resources such as the file system, XPC services, and system calls, and it's implemented all the way into the kernel. Each sandbox profile represents a set of rules. Knowing these rules gives us a clear picture of what the system permits or denies. This helps guide our efforts more efficiently. Imagine you're developing an exploit, I hope you're not, but let's say, that needs to access a protected data on the device. Without knowing the sandbox rules, you could spend weeks building and testing your exploit, only to realize later that the sandbox completely blocks this action. So instead of trial and error, you can check the rules in advance and immediately see whether your approach is even possible. If the sandbox explicitly blocks what you need, you can pivot early and save a lot of time. Also, different processes have different profiles. So by analyzing them, you can make smarter decisions about where to focus your research. So the end goal here is to decompile the sandbox profile. So what do we already have? We have an old implementation of this exact process, a tool called Sandblaster. As stated in the README, Sandblaster is a tool for decompiling Apple Sandbox profiles. Apple Sandbox profiles are written in SBPL, which stands for Sandbox Profile Language, and then compiled into an undocumented binary format. So basically, it reverses those binary profiles back to their original SBPL representation. The only problem is it supports up to iOS 11. So for reference, when I started this project, it was already iOS 17 and almost iOS 16 and almost 17. So obviously things had changed a lot. But now, what is the first thing you do when extending an old tool? Of course, you run it and see what happens. Reading through the README, we can see Sandblaster takes 3 arguments. One of them is the output folder, so we are actually only missing 2. These 2 are the Sandbox operations and the Sandbox bundle. The Sandbox bundle, which is the actual profiles data, is located in the kernel Sandbox extension in binary format. It's referenced by a function called hook policy init, which is the function that initializes the Sandbox profiles at runtime. Looking at hook policy init, we can see a panic string that says, failed to initialize platform Sandbox. Right above that, we can see a pointer to the const section in the Sandbox text, and that pointer leads directly to the binary blob that contains the profile data. Below it, we can also see the size field. So with that, we can extract the Sandbox profile data. That gives us one of the arguments we need. The second argument we need is Sandbox operations. These Sandbox operations are basically the system calls or action that the Sandbox restricts. To locate them, we search for known operation names inside the Sandbox kect. This will lead us to the list of operation names inside the const section. The content of the list also can change across iOS versions. With that, we have all that Sandblaster needs. So after taking these steps, I was really hoping it would just work. But of course it didn't. The file format changed dramatically. Sandblaster worked great up through iOS 11, but for iOS 16 and above, it simply couldn't parse things correctly anymore. The gap was way too large. But still, it gave me a solid starting point because it already handled a complex parsing logic. So if I could just adapt it to read the new file format, the rest would still work. So let's leave the file format for a second and move on to understanding the output. So again, iOS Sandbox profiles are basically defined a set of rules. For example, in this example, we can see that if we want to use dynamic code generation, you must have dynamic code signing entitlement. As we know, entitlements are those key value pairs that define which permission a process has. Without the right entitlement, the Sandbox simply blocks this action. So basically, the challenge is taking the binary format and turning into a human-readable list of rules. This is what we use Sandblaster for. To do that, I use 2 complementary approaches. First, I would compile Sandbox profiles myself to see how specific scenarios are encoded. And the second is reverse engineering the kernel to see how the kernel actually processes them. Each approach serves a different purpose. The first is for testing and validating specific scenarios, and the second helps us fully understand the parsing logic. Analyzing the kernel, we can see that there are 3 main profile types: the platform profile, the built-in collection, and the protobox collection. Each one has a different structure and a different parsing routine, and it's interesting to know that the platform profile is evaluated before both of them during execution. The analysis also showed that the Sandbox is parsed and evaluated dynamically. The main functions involved are Sandbox evaluate, evaluate operation, and evaluate. These are the core evaluation routines that decide what actions are allowed or denied during runtime. So let's return back and dive into the file format itself. The file format divides into several sections. The header section, which contains the profile type and key metadata. the operations section, which is a table of all the operation that the sandbox restricts, the operation nodes, which define the actual rules or decision points, and finally, the literal section, which holds all the string data, compiled regex, pattern, bitmaps, and everything that's used in the rules. Zooming in on the header, it contains the profile type, which can be single or collection, the total number of operation nodes, these are the rules or decision points I mentioned earlier, and the number of operation, which are the system called action we extracted from the sandbox text, and other structural metadata that describe the file. Here is a small example profile. I compiled it to show what it looks like in binary form. It has only one rule: deny dynamic code generation if a process doesn't have dynamic code signing entitlement. Here we can see the binary output. Now, bear with me because it's a lot of words, I know, but I will keep it short. So the orange is the number of operation nodes. Each one is 8 bytes long. The blue represents the operation nodes themselves. Here we have 3. We have one for allow, one for deny, and one for checking the entitlements. Green is the number of operations, and gray is the operation table, where each entry points to one of the blue nodes. The purple stands for, the small purple there stands for dynamic code generation. I know it because it's at index 10 in the table, which matches the same index in the kernel's operation list we've extracted earlier. The purple operation points to node 0. Operation nodes act like decision points. So if the rule at node 0 matches, execution jumps to node 2. Otherwise, it will jump to node 1. This process continues until a final allow or deny is reached. That's why compiling your own profiles is so useful. You can just test small cases like this and apply the logic to a larger, more complex profiles. It really helped me with the new iOS 18 implementations. Now let's talk a little bit about collection profiles. These are also initialized in hook policy init, but have a type ID of 80. They are basically bundles of multiple profiles, each with its own operation table and metadata. For example, a collection might include profiles for process A, process B, and process C. When we decompile it, we can extract the sandbox rule for each individual process, process A, process B, and process C. If we zoom in into the collection, each profile has its own operation table, like the gray section we saw earlier. And they are stored sequentially, one after another. Each profile also contains a pointer to its process name, so we can directly associate a profile to its process. So we are done with the bytes part, and now we can parse profile and get the decompiled SBPL. And that's really, really great, but still very hard to read. It's fine for simple, small rules, but once the logic grows, the SBPL becomes almost unreadable. These nested conditions and long chains make it impossible to follow and really ugly. That's when we started thinking, how can we make it easier to understand? My peers suggested to build a tool that does exactly that, but I think we managed to think on something easier. So one of my peers had a great idea. These rules are basically just if-else statements. So instead of outputting SBPL, why not translate them into C code as if-else statements, compile it, and then decompile it with any decompiler we like. This way, instead of developing a new tool, we can take advantage of the tool we are already familiar with. And we added this feature to Sandblaster, and the results were much clearer and easier to read. It was amazing. This is what the results look like. Each operation becomes a function. Each function of these returns allow or deny. So now you can simply just read the decompiled C code and follow the logic step by step. It made the output much easier to understand and the work made much easier. But then I started getting questions. Okay, this is great, but how do we extract the Sandbox profile in the first place? That process, as you remember, isn't that simple. It requires some knowledge of the Sandbox text code. So another peer of mine, the one that asking those questions, built a tool that automates this entire process. It automatically downloads the correct kernel, extracts the Sandbox blob, and parses them. And honestly, that was my main goal publishing this Sandblaster fork, to make this tool community-driven so people can share knowledge and contribute code, because a lot of us need it, but don't have a lot of time to invest in it. Then became iOS 18. At first, supporting it wasn't a priority because, well, this is tooling, which isn't as exciting as finding new vulnerabilities, but still, tools like this are critical for progress. Investing in tooling is what makes the rest of the research even possible. So what changed in iOS 18? In short, a new collection profile called Autobox was introduced. It seemed to be just Protobox with a new name. Some minor structural changes in the format were made. Also more filters, which are the conditions, were added. And most importantly, 2 new actions were added. So apart from allow and deny, we now have allow, deny, autobox, and delegate. Also, there is a new data type that got used extensively, which is bitmasks. So mostly used to define rules for a group of syscalls or commands. In addition, collection profiles now reference base profiles. Most use the same base profile called baseline, but a few uses a different one. So take it into consideration when you look at a profile from built-in collection. Check the baseline profile to evaluate it as well. This is another example of how Apple evolving the sandbox. This constantly challenges us to improve our tool and share our knowledge. This is part of why my goal here is to shed some light on this subject. And that brings me to where we are now. There is still so much I want to understand on this mechanism. Also, this Sandblaster fork is not yet bulletproof, but my goal is to make it easier to use and powerful as possible. And with the help of my peers and everyone who wants to join, that can totally be achievable. I really, really love this project. I will keep researching it. I invite you all to play with this tool, explore it, and share your findings. Thank you. Thank you. I would like to first of all, to the owner of Sandblaster. Thank you for all the work he did. I'm using a lot of blacktop tools. They really helped me a lot, so thanks to him too. I hope you enjoyed, and I hope I've managed to give you some head start in researching iOS Sandbox, and mostly, again, give you the information I was missing when I started. So for questions, please do approach me after the talk. I will be happy to hear you and talk about iOS Sandbox. There is a lot more to research on this subject and a lot more to talk about, I know, but all of this for next time, and thank you very much.